Hello everyone. In this video we're going to prove this introductory fact from real analysis. It's one of the first things you prove after you look at the definition of R, which we'll mention. And we also think about the supremum. And so we take R essentially, we'll look at this, right? R is the set that is a complete ordered field, right? So complete in the sense that every subset has a supremum. Okay, so I'll write that complete ordered field. Okay, and the complete here means that every subset has a supremum. Let's remind ourselves what the definition is of a supremum. Right, so definition. Right, we have that a real number S is a supremum of a set A, which is a subset of the reals, if one, we have that S is an upper bound for A, and if it's the least upper bound, right? So if B is any upper bound for A, then B is then S is less than or equal to B, right? S, this number S is the work which we're claiming is the supremum, is the least upper bound. So if we think about the set, the open interval 0 to 1, then the supremum, right? Call that A maybe. The supremum of A is 1, right? So it is an upper bound for this set. Every element of this set is smaller than or equal to 1. And if we take any other upper bound for this set, then it is greater than or equal to 1, right? What's another upper bound for this set? 5 is an upper bound for this set, right? But like 0.9 is not an upper bound, so it is not less than or equal to this number. Greater than or equal to, it is less than. Okay, so we're proving this fact here. Suppose S is an upper bound for some set, so we know it's an upper bound. Then we want to show that it's the supremum. So it is the supremum. So we take that as upper bound. It has to be an upper bound. But it is specifically the supremum of a set, if and only if, and then this condition right here. So what is it saying? It's saying that for all epsilon greater than 0, there is some A such that A is greater than S minus epsilon. So what does that mean, right? So we have our interval, right? Let's just think of our A as an interval. Okay, so A is not necessarily an interval, but let's just think of it for this example, right? So A is, here's our real number line. And then we think of our interval maybe as being from 0 to 1. Right? It could be the open interval 0 to 1. Then we say that, this 1 is the supremum because if we think of any amount lower, right? So this would be maybe 1 minus epsilon right there, right? And that distance there maybe being epsilon. If we think of our set as, so this little distance in here being epsilon, if we choose any value for epsilon, there will always be some number in there, right? There will always be some number in there. So there will always be some A, right? That's in there. So if I choose epsilon to be, for example, epsilon is 0.1, then I'm thinking about all the numbers that are between 1 minus 0.1 and 1, right? And there's lots of numbers in there, right? 0.9 and 1, lots of real numbers in there, right? So example A equals 0.95. So it's basically saying like we can squeeze ourselves, the supremum is like we've squeezed ourselves right up to the brim of possible upper bound values. Okay, so this is the smallest possible upper bound, which is clearly what it is, but we formally prove this statement. Okay, let's get into it because stop talking about it and actually do it, right? So it's if and only if, so we need two directions, right? We have the forward direction, which is to suppose that S is a supremum, and then we show this. Okay, well, that's not too hard, so let's do that. So we have our forward direction. So we suppose S, first of all, is an upper bound. That's just throughout this whole example, S is an upper bound for a subset, which is a subset of the real numbers. Not necessarily an interval, but just a subset. And and S is equal to the supremum of A. So now we show that for all epsilon greater than 0, there exists an A in A such that A is bigger than S minus epsilon. Okay, so sure. So fix epsilon. Consider so we fixed epsilon. Now consider the number. Consider the number S minus epsilon. Right. Well, since S, maybe move to the next line here. Since S was the supremum of A, then by definition, S minus epsilon is not an upper bound for A, right? Because S minus epsilon is less than S. Epsilon is some positive number. So S minus epsilon is not an upper bound anymore. Well, it's not an upper bound. Okay, therefore, there exists some A in A. So it's not an upper bound for A, right? So there exists an A in A such that A is greater than S minus epsilon. I mean, it basically just kind of falls out of it because S minus epsilon is no longer an upper bound. The supremum was the least upper bound. So any value less than it surely is not an upper bound. Okay, so that's all that we have in that direction. And now let's take a look at the other direction. Maybe I'll choose a light blue or something here. Right, so let's say I have the reverse direction. So now we suppose the conclusion here, right? So we have that for all epsilon greater than 0, there exists an A in A such that A is greater than S minus epsilon. And we show that S being an upper bound, therefore, including this, we also have that S is the supremum. So suppose S is an upper bound for some subset A, which is a subset of R. Also, that for all epsilon greater than 0, there exists an A in A such that A is greater than S minus epsilon. We need to show S is the supremum of A. Well, what does that mean for it to be the supremum? Let's go back to our definition. It's an upper bound for A. Good, we already have that, right? So we don't have to check that first thing. But the second thing we have to check, if B is any upper bound for A, then S is less than or equal to B. Okay? And so all we need to show is that if B is an upper bound for A, then B is less than or equal to S. Sorry, other way around. S is less than or equal to B. We can proceed by contradiction here, right? So maybe I'll change my color up and I say, by contradiction, contradiction, suppose B was greater than S, less than S. Strictly less than. Well, if B is less than S, this implies that B equals S minus epsilon for some epsilon greater than 0. Right? If it's less than, then it must be the number minus something. Well, we know, right, from this fact that for all epsilon greater than 0, there exists an A in A such that A is in that little range there. So by, we'll call that maybe star or something, by star, there exists an A in A such that A is greater than B, let's say. Therefore, B is not an upper bound. Okay, and I'm realizing you can't really see the epsilon, but this is epsilon greater than 0 there, right? So not an upper bound. For A, which contradicts that. Okay, so we have a contradiction. Oops, contradiction. Therefore, B is greater than or equal to S. Okay, and that concludes the proof, the overall proof here.